Right folks, we're going to make a quick start. We're going to be talking about alpha, beta and gamma radiation during next lesson. Bear in mind this is the first trial of the flipped classroom project, so if you don't understand any part of this video, make sure you view it at least a couple of times so that you're well aware of the stuff that you need to know before the lesson. In the lesson we're going to be talking about alpha, beta and gamma radiation. You need to know the nature thereof, and you also need to be able to detect which ones come from each sample, because we're going to be using different samples in the lesson. Now, the nature of them. First of all, you need to represent them with certain symbols. The symbol for alpha is this symbol. It's like a fish without the tail end on it. There's a beta, which is a B with a tail on it, and gamma. Gamma is a traditional symbol for radiation. It's a Greek letter, as with all of them. And this symbol, also you might have seen, it's a symbol for cancer as well. So, as it represents, it does cause cancer, as do the rest of them. So that's where this symbol comes from. It's the Greek letter gamma. Right, the nature of them. Basically, alpha radiation is a 4-particle piece of radiation all bound together. You've met these particles before. Inside of an atom, there are protons, neutrons, and electrons. Now, you might remember, might be a bit hard to see that. You've got protons and you've got neutrons inside of the nucleus, and you've got electrons going around the outside. Now, these protons give the atom charge, the neutrons give it stability, they have no charge, and you've got these electrons going around the outside. And when we did chemistry, the atom explained a lot of the fundamental processes that go within compounds. So we talked about ionic bonding, we talked about covalent bonding, and we talked about ways that these things stick together. But now we're talking about other parts of atoms. When you've not got a complete atom, it's unstable. So we call it radioactivity. Now, when you've got 2 protons and 2 neutrons stuck together floating through space, we call that an alpha particle. So this here is an alpha particle. When you've just got an electron, which is the bit from the outside of the atom wandering around, that's the beta particle, which is this one. And the final one is a gamma ray. Now, a gamma ray is not a particle. A gamma ray is a particle, it's not a particle, it's a wave of light. And that wave of light travels through space at the speed of light. But it's very different to light. It's not like light that we see under normal circumstances. Gamma rays are incredibly high energy forms of light. So these carry lots of energy and they do lots of damage. They can pretty much go through anything. So they go through pretty much everything except very thick lead. So you can shield yourselves against these, but we'll talk about the shielding process in a bit. This one being a gamma ray. Now be careful not to refer to this one as a particle like I just did. These two are particles, this one is a ray. They are different, they're mutually exclusive. Now, you need to be able to identify them. It's fairly easy to tell them apart if you know the nature of them. We'll start off with the alpha particle. What we know about the alpha particle is basically the alpha particle has a charge. You've probably noticed that there's 2 protons in there, and as we talked about in chemistry, protons have a positive charge. Neutrons are neutral. That means 0 charge. And electrons have a negative charge. So we should be able to figure out the charges of these individual pieces of radiation. So we'll start off with the alpha particle. The alpha particle's got 2 protons in it, so obviously it's got 2 pluses, so the charge on an alpha particle is 2 plus. The beta particle is 1 electron, so its charge is 1 minus. The gamma ray is not a particle, so it's got no bits in it to make it charge. Therefore, it just travels through space with a 0 charge. No charge either way. Now, if you pass all of this radiation through 2 charged plates, sorry, 2 plates of metal, and I charge them up with electricity, and I've got positive on one side and negative on the other side. As you learned in year 7, I think it was, like charges repel each other and opposite charges attract. So when an alpha particle, let's just say we've got a mystery particle, there it is, it goes in, and inside there it's going to be attracted or repelled by one side. Its charge is positive. Because its charge is positive, it's repelled by the positive side and attracted by the negative side. So it moves like that and hits the negative plate, and we know that's an alpha particle. The beta particle, let's just say that's that one, we'll give it a symbol for alpha. This one being the beta particle, as you probably guessed with that one, as it goes in, it's attracted to the positive plate because the charge is negative, opposites attract. The gamma ray goes through, no problems whatsoever, it's no charge, so it's not attracted to either plate. So that's a way of telling what type of radiation that you're dealing with. If you've got an alpha particle, it sticks to the negative plate. If you've got a beta particle, it sticks to the positive plate. If you've got a gamma ray, it passes through these plates with nothing happening. Right, we're going to move on to the last bit, which is protecting yourself. Now, once you know what type of radiation that you're dealing with, it's kind of important that you can protect yourself from them. So we'll talk about alpha first. Now, alpha, as we just talked about, is 2 protons and 2 neutrons, which makes it very, very highly charged, and it's also very, very heavy, well, compared to the rest it is. So it doesn't get through very, very much. If you want to absorb it, it's absorbed by about 5 centimetres of air. So if I was standing roughly the same distance away from the board as I am now, I'd be safe even if it was emitting alpha radiation. Alpha radiation is used all the time, and as long as it's kept at a reasonably safe distance, it's fine. If you want to really, really mess it up though, just put some paper over it. There's no way it's going to get through paper, so a bit of paper over the top and you're safe. The beta radiation. The beta radiation is an electron, so we can think about it as a flow of electric charge. Now, an electric charge is absorbed by metal. You know that metals carry electronics. So, if you put metal, let's just say it's some aluminium foil, in the way, so you put your tin hat on or whatever, then that protects you from beta radiation. Now, if you wanted to protect a source or you protect a detector from beta radiation, all you just do is cover it in aluminium foil. It's done. Problem solved. The last one's gamma radiation. Gamma radiation is a nightmare to try and stop. It goes through pretty much everything. It's a very, very high energy wave. There's no charge on it, so it just pretty much passes through things, no problem. You need some really thick lead. I mean, really thick lead to be able to stop that. We're talking meters of it. They use concrete sometimes because it's quite dense, but it still doesn't work as well as lead, so we keep gamma radiation in lead lockers. I think that's pretty much everything that you need to know regarding the absorption and protection from them. The last thing that we need to cover is the dangers of them. Now, alpha radiation. Back to the beginning, alpha radiation is really, really dangerous because if it gets into your body, it doesn't have to travel through anything, it doesn't have to travel through air or paper or whatever, it gets straight into your cells. And because it's got a really high charge, it strips electrons from your body and causes mutations, so it causes massive cancers. And that's called ionisation. Make sure you spell that one right, that's a key word when we come to the lessons. Ionisation. Its ionisation is incredibly high. Incredibly high. So it really, really damages your cells. Beta, because it's got a negative charge, its ionisation is fairly moderate. Yeah. We say it's medium/moderate. That means that it's fairly good at ionising your cells. It's not quite as good as alpha though, but its range is greater. So all in all, beta is the most dangerous all around because it's quite ionising and it's got a better range than alpha. But if alpha gets into your body, you're stuck. Right, the last one is gamma radiation. Gamma radiation, its ionisation is very, very low because it has no charge. So its ionisation, even though it's low, can still be quite dangerous in high dosages. If you end up with a lot of gamma radiation, it's an issue. If you end up with not much of it, its ionisation is low so it doesn't cause too many problems. So you know how to protect yourselves. We're talking about paper, aluminium foil or metal, and thick lead. talks about which one's the most dangerous where. This one's dangerous in high doses because there's fairly low ionisation. This one is pretty much dangerous all the way around, but it's not the worst. This is the worst, but it's got short range, so if it gets into your body, you're stuffed. If it's outside of the body, it's absorbed by your skin, which is no problems whatsoever. Day in, day out, the amount of radiation that you're going to be exposed to, more than likely is going to be gamma. So it does cause cancer, all of these cause cancer, but you know how to protect yourselves now. So when you come into the lesson, when we do our first flipped classroom investigation, we're going to be looking at these three types of radiation. We're going to be doing some experiments on them. You're going to be identifying which ones are which, and then you're going to be putting some safety guidelines in place to handle each one of these three. Okay? That should pretty much cover everything that you need to know about them. If you need to ask any questions, then you can enrol on Modo, or you can come and ask me before the lesson. But please make sure you are prepared beforehand, because the next part is the practical investigation, and it can get messy.